In this chapter, we zoom into physical file organization and indexing. It is based upon our book, Principles of Database Management, published by Cambridge University Press. You can find more information about our book on the website at the bottom of my slide. My name is Bart Baasens, and I'm one of the authors of the book. This chapter focuses on the most important principles pertaining to the physical organization of records and files. First, we present some overall properties of storage devices and the impact of the mechanicals of hard disk drives on the performance aspects of data retrieval. After that, we overview the mapping of logical modeling constructs onto physical concepts and thus of the logical data model onto the internal model. Then, we briefly discuss record organization, covering the different alternatives to organize physical data records consisting of individual data fields. After that comes the main body of this chapter, focusing on file organization and covering methods to organize records into physical files as well as techniques to efficiently search for records with certain characteristics. We discuss several approaches, such as sequential files, hashing, and the use of different index types, including B+ trees. Physical database design pertains to the design of an internal data model and to the way in which logical database concepts are realized physically as stored records, physical files, and ultimately a physical database. In this chapter, we assume a relational database setting unless noted otherwise. In what follows, we discuss the storage hierarchy, internals of hard disk drives, and how to translate logical concepts to physical constructs. A computer system's memory can be looked upon as a hierarchy as shown here, with high-speed memory that is very expensive and limited in capacity at the top, and slower memory that is relatively cheap and much larger in size at the bottom. The top of the storage hierarchy is the central processing unit, CPU, with its registers, in which the mathematical and logical processor operations are executed. Most often, some high-speed cache memory is physically integrated with the CPU and/or with the motherboard that contains the CPU. Cache memory operates at nearly the same speed as the CPU. Below that, we have central storage, which is also referred to as internal memory or main memory. It consists of memory chips, also called random access memory or RAM, of which the performance is expressed in nanoseconds. Each individual byte in central storage has its own address and is directly referable by the operating system. The entirety of the memory described so far is called primary storage. This type of memory is considered volatile memory, which means its content is cleared when the power is turned off. Volatile memory certainly has its role in a database system, as it contains the database buffer as well as the runtime code of the applications and DBMS. The memory we will focus on in this chapter is secondary storage, which consists of persistent storage media, retaining its content even without being powered. The physical database files reside in secondary storage. The most important secondary storage device is still the hard disk drive, HDD, although solid-state drives, SSD based on flash memory are catching up quickly. Primary and secondary storage are divided by what is known as the I/O boundary. This means that all memory above this boundary, although slower than the CPU, still operates at speeds that make it efficient for the CPU to wait until data is retrieved from primary storage. In comparison, secondary storage is much slower. The speed of HDDs and SSDs is typically expressed in milliseconds. It is not efficient for the CPU to wait until the interaction with secondary storage is completed. Rather, the CPU will switch to another task or thread until the requested data is copied from secondary storage to primary storage, or until data that was manipulated in primary storage is persisted onto secondary storage. The exchange of data between secondary storage and primary storage is called I/O, input-output, and is supervised by the operating system. The operating system signals when the I/O task is completed, such that the CPU can continue processing the data. Still lower in the hierarchy, we have even slower storage technology, such as optical drives, for example, rewritable DVD or Blu-ray, and tape, which mainly serve as medium for backup and archiving rather than being considered a directly accessible layer in the storage hierarchy. In what follows, we assume a hard disk drive as the storage medium for the physical database. Hard disk drives store their data on circular platters, which are covered with magnetic particles. An HDD also contains a hard disk controller, which is circuitry that oversees the drive's functioning and that interfaces between a disk drive and the rest of the system. Reading from and writing to hard disks comes down to magnetizing and demagnetizing the spots on these platters to store binary data. Hard disk drives are directly accessible storage devices, DASDs, which means that every location on a platter should be individually addressable and directly reachable to access its content. Since a platter is two-dimensional, movement in two dimensions should be supported by the hard disk drive's mechanicals. The first dimension of movement is disk rotation. For that purpose, the platters, or sometimes only a single platter, are secured on a spindle, which rotates at a constant speed. Movement in a second dimension is realized by positioning the read-write heads on arms, which are fixed to an actuator. There is a set of read-write heads for each writable platter surface. The actuator, along with the arms and the read-write heads, can be moved towards or away from the center of the disks. Here you can see a figure illustrating the internals of a hard disk drive. By combining disk rotation with actuator movement, each individual section of the disk is directly reachable. The magnetic particles on the platters are organized in concentric circular tracks, with each track consisting of individual sectors. The sector is the smallest addressable unit on a hard disk drive. Traditionally, the standard sector size was 512 bytes, but many more recent HDDs have sector sizes of up to 4,096 bytes. Also, for reasons of efficiency, it often occurs that the operating system or the HDD itself doesn't directly address individual sectors, but rather addresses so-called disk blocks, also known as clusters, pages, or allocation units, which consist of two or more physically adjacent sectors. By addressing disk blocks encompassing multiple sectors, the number of required addresses and the amount of overhead can be reduced. In what follows, we make abstraction from these distinctions and always use the generic term disk block, or block for short, to refer to an addressable unit of hard disk storage capacity consisting of one or more adjacent physical sectors. Reading from a block or writing to a block identified by its block address comes down to the following. First, the actuator needs to be moved in such a way that the read-write heads are positioned above the track that contains the desired block. The time necessary to position the actuator is called the seek time. All sectors on the same track of a platter can then be read without additional seeks. Moreover, since all read-write heads are positioned on arms above one another, all tracks at the same distance from the center on the respective platter surfaces can be read without additional seeks. Such a set of tracks with the same diameter is called a cylinder. Once the heads are positioned appropriately, one must wait until the desired sector has rotated under the read-write head of that platter surface. The time required for that is called the rotational delay or latency. Finally, the data can be read or written. The transfer time depends on the block size, the density of the magnetic particles, and the rotation speed of the disks. The response time to retrieve a disk block from a disk drive can be summarized as follows. Response time equals service time plus queuing time, and service time equals seek time plus rotational delay plus transfer time. Physical file organization can be optimized in such a way that the expected seek time and, to a lesser extent, rotational delay are minimized, and this may have a considerable impact on overall performance of a database system. For that reason, we discriminate between the expected service time for random block accesses, TRBA, and the expected service time for sequential block accesses, TSBA. TRBA refers to the expected time to retrieve or write a disk block independently of the previous read or write. TRBA equals seek plus ROT divided by 2 plus BS divided by TR, with block size BS, rotation time ROT, and the transfer rate TR. TSBA denotes the expected time to sequentially retrieve a disk block with the read-write head already in the appropriate position from a previous read-write to a physically adjacent disk block. TSBA equals ROT divided by 2 plus BS divided by TR. For a hard disk drive with the characteristics depicted in the table, we have TRBA equals 8.9 milliseconds plus 4.167 milliseconds plus 0.026 milliseconds equals 13.093 milliseconds. TSBA equals 4.167 milliseconds plus 0.026 milliseconds equals 4.193 milliseconds. From this example, it is recommended to organize physical files onto tracks and cylinders in a way that seeks and, to a lesser extent, rotational delay are minimized as much as possible. This objective is a leading theme throughout most of this and the next chapter. Physical database design comes down to the translation of a logical data model into an internal data model, also called the physical data model. This translation takes the physical properties of the storage media into account, as well as the statistical properties of the data and the types of operations, such as search, insert, update, delete, that are executed on them. The internal data model should provide adequate support for the most frequent and our most time-critical operations. The figure below recapitulates the three-layer database architecture and the position of the internal data model in it. As discussed previously, this approach guarantees physical data independence. An optimal trade-off is pursued between efficient update or retrieval and efficient use of storage space. The main focus is on the physical organization of structured data by translating logical structures into physical ones. This table lists the various corresponding concepts. In general, a logical model defines entity records, or just records for short, as instances of entity record types, or record types for short. A record is described by its attributes. In a relational setting, we speak of a logical database as a set of tables or relations. A table consists of rows or tuples which contain values, also known as cell values, as they represent values to the individual cells in a relational table, described by the corresponding column names. The corresponding physical concepts are represented in the last column. A data item, also called field, is a collection of bits or characters that represents a specific value on a physical storage medium. A stored record is a collection of data items that pertain to the same real-world entity and that represent all attributes of this entity. In this way, it is the physical representation of a tuple in a relational table. A physical file, also called dataset, is a collection of stored records that represent similar real-world entities, such as students, wines, or purchase orders. It implements a relational table, or in general, all instances of a logical record type. In most cases, all records in a physical file have a similar structure and contain data items that represent the same set of attribute types. Physical files may contain additional structures, such as indexes and pointers to efficiently search and/or update the file and its contents. Finally, a physical database, also called stored database, is an integrated collection of stored files. In this way, it contains data items and stored records describing different kinds of real-world entities, for example, suppliers and purchase orders, as well as their interrelationships. For example, the fact that a particular purchase order is placed with a particular supplier. The logical structures that model the relationships between record types, such as the foreign keys in a relational model, also yield a physical representation. A stored database contains physical storage structures to represent these logical interrelations, as well as to support the efficient retrieval and manipulation of stored records according to these interrelations, for example, to execute a join query in a relational setting. This figure shows an example of a simple conceptual data model, which is translated into a relational logical model and ultimately into an internal data model. The relationship type between a supplier and his or her corresponding purchase orders is represented by means of a foreign key in the relational data model. In the internal data model, it is implemented by storing a supplier record physically adjacently to its purchase order records. If supplier records and the corresponding purchase orders are often retrieved together, this contiguous organization is beneficial, as they can be retrieved with a consecution of sequential block accesses, thus avoiding more inefficient random block accesses. In addition, a separate index is provided which allows you to efficiently look up the supplier one is interested in. The latter refers to the suppliers not by means of physical contiguousness, but by means of pointers. Record organization refers to the organization of data items into stored records. Each data item embodies an attribute of a particular real-world entity that is represented by the stored record. The physical implementation of the data item is a series of bits. The actual format depends on the attribute's data type. In what follows, we discuss the following techniques: relative location, embedded identification, and use of pointers and lists. The simplest and most widespread technique for record organization is relative location. Here, only the attributes are stored. The data items that represent the attributes of the same entity are stored on physically adjacent addresses. The corresponding attribute types are not stored with them. They are determined implicitly by the relative ordering in which the data items occur based on metadata about record structure in a catalog. In this way, each data item can be identified by its relative location. This figure shows a partial relational table definition and the corresponding record structure. In case of embedded identification, the data items representing attributes are always preceded by the attribute type. Only non-empty attributes of the record are included. See the figure. Because the attribute types are registered explicitly, missing attributes are not a problem, and there is no need to store the attributes in a fixed order to identify them. The obvious disadvantage is the extra storage space required for the attribute types. But for highly irregular records, this approach is still more efficient than relative location. The third option is to use pointers and lists. These are discussed in more detail in later sections on file organization, but can also be used for the sake of record organization. There are different possibilities. The figure shows an example where only attributes are stored. There is a regular record structure except for the fact that the number of addresses may be different for each person. Therefore, for each person, one address is stored physically adjacent to the other data items. But if a person has multiple addresses, a pointer is included that refers to the storage location where the other addresses are positioned. In this way, irregularities can be dealt with without affecting the overall record structure. Another important concept is the blocking factor, BF. The latter indicates how many records are stored in a single block. For a file with fixed length records, BF is calculated as follows: the floor of BS divided by RS. BS denotes the block size and RS is the record size, both represented in bytes. The floor function rounds down the value to an integer. For variable length records, BF denotes the average number of records in a block. The blocking factor is an important value when organizing physical records for efficient access, as it determines how many records are retrieved with a single read operation without intermediate seeks and/or rotational delay. Physical file organization pertains to the organization of stored records into physical files or datasets. We first introduce some introductory concepts such as search keys and the distinction between primary and secondary file organization before tackling the actual file organization techniques listed here. The records in a physical file are organized in such a way that they can be retrieved efficiently according to one or more search keys. A search key is a single attribute type or set of attribute types whose values determine the criteria according to which records are retrieved. A search key can be a primary key or candidate key, in which case the search key only yields a single result, since no two stored records can have the same primary or candidate key value in a physical file. Examples of such unique search keys are a customer ID, a license plate number, the combination of a flight number and the date of departure, etc. Although primary keys are often used to retrieve data, a search key can just as well consist of one or more non-key attribute types. Indeed, one often needs to define data according to other criteria, which do not represent unique identifiers. For example, the class of a flight, seat, such as economy class, business class, first class, etc., is a search key that can be used to retrieve seats, but the result is not necessarily unique and may contain many seats. A search key can be composite. For example, the search key country and gender with values US and F yields all female customers that live in the US. Finally, search keys can also be used to specify range queries. These are queries that retrieve all records where some attribute value is between a lower and upper limit, such as all customers with a search key value for year of birth between 1980 and 1990. We distinguish between two categories of file organization methods. First, there are methods that determine the physical positioning of stored records on a storage medium. We call them primary file organization methods. The examples we discuss are heap files, random file organization, and index sequential file organization. Some methods require a linear search on the entire file for records that match the search key. Each record in the file is retrieved and assessed against the search key. Yet, the more advanced methods specify a relationship between the record search key and its physical location. This improves retrieval speed considerably as it allows directly accessing the storage locations that contain records that correspond to the search key, thus avoiding a linear search. Hashing and indexing are the primary techniques to establish such a relationship. When implementing a physical file, the primary records When implementing a physical file, the records are physically organized according to the primary file organization method. Since the primary file organization impacts the physical ordering of the records, we can apply only one primary file organization on a particular physical file, at least if we want to avoid duplicating the file. Secondary file organization methods provide constructs to efficiently retrieve records according to a search key that was not used for the primary file organization. Secondary file organization methods do not impact a record's physical location and invariably use some kind of index called secondary index. The most basic primary file organization method is the heap file. New records are inserted at the end of the file. There's no relationship between the record's attributes and its physical location. Consequently, adding records is fairly efficient, but retrieving a particular record or set of records according to a search key is not. The only option is to do a linear search, scanning through the entire file and to retain the records that match the selection criteria. If a single record is sought according to its primary key, the scanning continues until the record is found or until the end of the file is reached, meaning that the record is not present. For a file with NBLK blocks, it takes on average NBLK divided by 2 sequential block accesses to find a record. Still, the more requests occur for records that turn out not to be in the file, the more searches will happen until the end of the file requiring NBLK block accesses. Searching records according to a non-unique search key also requires scanning the entire file, hence NBLK block accesses. Deleting a record often comes down to just flagging it as deleted. The records are then physically removed upon periodical reorganization of the file. With a sequential file organization, records are stored in ascending or descending order of a search key. This is often the primary key, but a non-unique search key can also be used as ordering criterion. An advantage this has over heap files is that it becomes much more efficient to retrieve the records in the order determined by this key, since it requires only sequential block accesses. Moreover, as with heap files, individual records can still be retrieved by means of a linear search, but now a more effective stopping criterion can be used, since the search key is the same as the attribute type or attribute types that determine the order of the records. If the records are organized in ascending or descending order of this key, the linear search can be terminated once the first higher or lower key value than the required one is found. If the sequential file is stored on a direct access storage device such as a hard disk drive, a binary search technique can be used, which in the case of large files is far more efficient than a linear search. A binary search algorithm is applied recursively, halving the search interval with each iteration. For a unique search key k with values ki, the algorithm to retrieve a record with key value k mu is as follows. First, selection criterion, record with search key value k mu. Set L equals 1, H equals number of blocks in the file, and suppose the records are in ascending order of the search key k. Then repeat until H bigger than or equal to L. I becomes L plus H divided by 2, rounded to the nearest integer. Retrieve block I and determine the key values kj of the records in block I. If any kj equals k mu, the record is found. Else, if k mu is bigger than all kj, continue with L equals I plus 1. Else, if k mu is strictly less than all kj, continue with H equals I minus 1. Else, record is not in the file. The expected number of block accesses to retrieve a record according to its primary key in a sequential file of NBLK blocks by means of a linear search is still NBLK divided by 2 sequential block accesses. If, on the other hand, binary search is used, the expected number is logarithm base 2 of NBLK random block accesses, which is much more efficient for high values of NBLK. Let's examine a sequential file with the properties shown in the table above. The blocking factor BF can be calculated in the following way. BF equals floor of BS divided by RS, which equals floor of 2048 divided by 100, which equals 20. Each block contains 20 records, and thus the required number of blocks NBLK to store the 30,000 records is 1,500. If a single record is retrieved according to its primary key by means of a linear search, the expected number of required block accesses is 1,500 divided by 2, or 750 sequential block accesses. On the other hand, if a binary search is used, the expected number of block accesses is logarithm base 2 of 1,500, which equals about 11 random block accesses. Even though random block accesses take more time than sequential block accesses, the binary search algorithm is much more efficient to search sequential files than scanning sequential files or heap files. Updating a sequential file is more cumbersome than updating a heap file, since now the records must be kept in order, and new records cannot just be added at the end of the file. Updates are often executed in batch. They are organized according to the same ordering attribute types as the actual sequential file, and then the entire file is updated in a single run. A possible alternative is to place newly added records as well as records for which the value of the ordering attribute types is updated in a separate overflow file, the latter organized as a heap file. Deleted records can just be flagged without being physically removed. In this way, the file only has to be reorganized periodically if the overflow file becomes too large. In a database setting, sequential files are often combined with one or more indexes, resulting in the index sequential file organization method. The latter is also discussed in detail later in this chapter. With random file organization, also called direct file organization or hash file organization, there exists a direct relationship between the value of the search key and a record's physical location. In this way, a record can be retrieved with one or at most a few block accesses if the key value is provided. This relationship described above is based on hashing. A hashing algorithm defines a key-to-address transformation such that the record's physical address can be calculated from its key value. Each time a new record is to be added to the file, this transformation is applied to its key, returning the physical address where the record should be stored. If later on the record is to be retrieved based on the search key, applying the same transformation to the key returns the address where the record can be found. This approach is most effective when using a primary key or other candidate key as search key. A key-to-address transformation consists of several steps as represented in this figure. First, the key is converted into an integer numerical format. Then, the actual hashing algorithm is applied, where the integer key values are transformed into a spread of numbers of roughly the same magnitude as the desired addresses. The more uniformly these keys are distributed over this range of numbers, the better. Note that, quite often, the generated addresses do not pertain to individual records addresses, but rather to a contiguous area of record addresses called a bucket. A bucket contains one or more stored record slots. Its size can be defined at will, but can also be aligned to the physical characteristics of the storage device, such as an integer number of disk blocks, tracks, or cylinders. The hashing algorithm can take on many forms, ranging from a simple hash function to more complex algorithms. However, it invariably consists of a consecution of mathematical operations applied to a numerical representation of the key and returning a hash value that corresponds to a bucket address. In the next step, this bucket address is translated into an actual block address. For that purpose, it is multiplied by a constant that compresses the generated hash values into the exact range of desired block addresses. The latter is still a relative block address, that is, relative to the first block of the file. A final step, which is governed by the file system and therefore can be considered beyond the scope of the key-to-address transformation, is a translation of the relative block address into an absolute address consisting of a device number, cylinder number, track number, and block number. Hashing cannot guarantee that all keys are mapped to different hash values, hence bucket addresses. Several records may be assigned to the same bucket. In that case, we speak of a collision, and the corresponding records are called synonyms. Collisions are not a problem per se, since a single bucket normally consists of multiple record slots, but if there are more synonyms than slots for a certain bucket, the bucket is said to be an overflow. Additional block accesses are needed to retrieve overflow records, and therefore overflow should be avoided as much as possible so as to not jeopardize performance. For that reason, a hashing algorithm should be chosen that distributes the keys as evenly as possible over the respective bucket addresses, thus reducing the risk of overflow. Division is one of the simplest hashing techniques, yet in most circumstances it performs remarkably well. With the division technique, the numerical form of the key is divided by a positive integer m. The remainder of the division becomes the record address. In other words, address key I equals key I mod m. Note that the mathematical operator that takes the remainder after a division is called the modulo, abbreviated as mod. The choice of m is very important. If m is inappropriate for the key set at hand, many collisions and therefore extensive overflow will be the result. Common factors between the key values and m should be avoided. For this reason, the chosen m is often a prime number. Most often, a prime number is chosen that is close to but a bit larger than the number of available addresses, yielding roughly as many values as the number of required addresses. This figure shows two series of key values, each time with the remainder of division by 20 and by 23. For the first series, both 20 and 23 result in a nearly uniform distribution of remainders and address values, so they would both be adequate as m. However, in the second series, division by 20 yields a much worse distribution, with many records attributed to bucket addresses 0, 0, 5, 10, and 15, whereas other buckets remain empty. Yet, division by the prime number 23 again results in a nearly uniform distribution. For a particular key set, one prime number may still perform better than another. So ideally, multiple candidates are tested. As said, most often a prime number is chosen that is close to but a bit larger than the number of available addresses, yielding roughly as many values as the number of required addresses. The efficiency of a hashing algorithm is measured by the expected number of random and sequential block accesses to retrieve a record. Several factors have an impact on this efficiency. Retrieving a non-overflow record requires only a single random block access to the first block of the bucket denoted by the hashing algorithm. It is possibly followed by one or more sequential block accesses if the bucket consists of multiple physical blocks. To retrieve an overflow record, additional block accesses are required. Hence, the percentage of overflow records as well as the overflow handling technique affect the performance. The former denotes how many records are in overflow. The latter determines where records that do not fit in a bucket as determined by the hashing algorithm are stored and how many block accesses are required to retrieve them. The percentage of overflow records depends on how appropriately the hashing algorithm is to the key set. In many cases, the key values are not distributed evenly. It is up to the hashing algorithm to map this irregularly distributed key set as evenly as possible onto a set of addresses. The aim of random file organization is to achieve a uniform distribution, spreading the set of records evenly over the set of available buckets because this would minimize the chance of overflow. Yet, in practice, the best performing hashing algorithms closely approximate the results of a theoretical random distribution rather than the ideal of a uniform distribution. The statistical properties of a random distribution can be used by the file designer to estimate the expected percentage of overflow records. Moreover, theoretically, a perfectly uniform distribution would require only as many record slots as there are records to be stored. Still, the reality of less than uniform distributions implies that more record slots are needed because some buckets are fuller than others, and the only way to avoid too excessive overflow is to provide more record slots than strictly necessary. The required number of buckets, NB, equals the ceiling of NR divided by BS times LF, with NR the number of records, BS the bucket size, and LF the loading factor. The trade-off here is that the larger the bucket size, the smaller the chance of overflow will be. On the other hand, a larger bucket means more additional sequential block accesses to retrieve all non-overflow records in the bucket. The loading factor represents the average number of records in a bucket divided by the bucket size and indicates how full every bucket is on average. In this way, the loading factor embodies the trade-off between efficient use of storage capacity and retrieval performance. A lower loading factor results in less overflow and hence better performance, but also more wasted storage space. A higher loading factor has the opposite effect. In practice, the loading factor is often set between 0.7 and 0.9 to balance storage efficiency with performance. The second main factor impacting the performance of random file organization is the way in which overflow records are stored and retrieved, known as the overflow handling technique. There are different approaches here, with overflow records being stored either in the primary area or in a separate overflow area. This figure illustrates how the combination of an inadequate transformation and inappropriate overflow handling may have a negative effect on retrieval performance. The simplified file contains 18 records with numeric keys 12, 14, 15, 19, etc. There are 10 buckets with a bucket size of 4. The blocking factor is 2 and each bucket spans 2 physical blocks. Suppose we use open addressing as a simple overflow handling technique. With open addressing, overflow records are stored in the primary area, more particularly in the next free slot after the full bucket where the record would normally have been stored according to the key to address transformation. A mod 10 key to address transformation is used, yielding 10 possible bucket addresses. The resulting key distribution is far from uniform and doesn't even come close to a random distribution, resulting in bucket 5 being overly stacked, whereas other buckets remain empty. Thus, despite the low loading factor of 0.45, we already have an overflow record. Indeed, the record with key 35 would normally have been stored in bucket 5, but since this bucket is already filled with other records, the next free slot is used in bucket 6. Retrieving record 35 now requires 1 random block access plus 3 sequential block accesses, whereas retrieving a non-overflow record would require at most 1 sequential block access in addition to the random block access. So indeed, overflow has a negative impact on performance. Moreover, so far, record 35 is the only overflow record, but if more records are added, record 35 may take up storage space of other records that would rightfully be directed to bucket 6 according to the key to address transformation. For example, a newly added record 86. Consequently, such records may also end up in overflow, resulting in a domino effect of more and more records being out of place and requiring additional block accesses for retrieval. An alternative overflow handling technique is chaining. Here, overflow records are stored in a separate overflow area, with subsequent records that overflow from the same bucket being chained together by pointers. Such a structure, where items are connected sequentially by pointers, is called a linked list. In the context of hashing, linked lists can be used to access all records overflowing from the same bucket by following the pointers between them. The advantage is that they do not clutter the primary area and therefore cannot cause additional overflow. The downside is that accessing linked list results The downside is that accessing linked lists results in additional random block accesses. As a closing note, dynamic hashing techniques exist that allow for a file to shrink or grow without the need for it to be completely rearranged. Random file organization is probably the most effective technique to retrieve individual records by their search key value. Sequential file organization is efficient if many records are to be retrieved in a certain order. An indexed sequential file organization method reconciles both concerns. An indexed sequential file organization combines sequential file organization with the use of one or more indexes. A file is divided into different intervals or partitions. Each interval is represented by an index entry which contains the search key value of the first record in the interval as well as a pointer to the physical position of the first record in the interval. Depending on the case, this pointer may be realized as a block pointer or a record pointer. A block pointer refers to the physical block access of the corresponding record. A record pointer consists of the combination of a block address and a record ID or offset within this block and refers to an actual record. An index itself is then a sequential file, ordered according to the search key values. The index consists of entries with the following format: search key value and block pointer or record pointer. The search key can be atomic, such as customer ID, or composite, such as the combination of year of birth and gender. A dense index has an index entry for every possible value of the search key that it indexes. Therefore, if the search key is a unique key, a dense index has an index entry for each separate record. If the search key is a non-unique key, if the search key is a non-key attribute type or combination of attribute types, a dense index has an index entry for every group of records with the same value for that attribute type. A sparse index, on the other hand, has an index entry for only some of the search key values. Each entry refers to a group of records, and there are fewer index entries than with a dense index. Dense indexes are generally faster, but require more storage space and are more complex to maintain than sparse indexes. Also note that an index file typically occupies fewer disk blocks than a data file and can thus be searched much quicker. With a primary index file organization, the data file is ordered on a unique key and an index is defined over this unique search key. An example is given in this figure. It depicts a file with intervals of 4 records. Each interval corresponds to a single disk block, hence the blocking factor is 4. The records are ordered according to the primary key customer ID. For each interval, there is an index entry consisting of the key of the first record in the interval and a pointer referring to the disk block that contains the records in the interval. There is an index entry for each disk block and not for each key value, so the index is sparse. To retrieve a record according to the required key value, say 12,111, a binary search is executed on the index to retrieve the pointer to the block that should contain the corresponding record, at least if it is present in the file. This is the third block in the example. In this way, instead of searching the entire file with data records, only the index and a single block of the actual data file need to be accessed. Either the record is found in that block or it isn't present in the file. We summarize the required block accesses for respectively linear search, binary search, and index search in this table. The expected number of block accesses to retrieve a single record using a primary index amounts to logarithm base 2 NBLKI random block accesses for a binary search on the index, with NBLKI representing the number of blocks in the index. One additional random block access is needed to retrieve the actual record, assuming the intervals correspond to individual disk blocks. Let's apply this to the same example as the one used for sequential file organization. In other words, a file consisting of 1,500 blocks and a block size of 2,048 bytes. Remember that the expected number of block accesses to retrieve an individual record by means of a linear search amounted to 750 sequential block accesses, whereas a binary search on the data file required only 11 random block accesses. If we assume index entries of 15 bytes, then the blocking factor of the index equals the floor of 2048 divided by 15, which equals 136. NBLKI is then ceiling of 1,500 divided by 136, or 12 blocks. A binary search on the index requires logarithm base 2 of 12 plus 1, or about 5 random block accesses. Moreover, indexing becomes even more advantageous in comparison to pure sequential organization as the file sizes grow larger than the one in the rather small file in the example. A clustered index is similar to a primary index, with the difference that the ordering criterion, and therefore the search key, is a non-key attribute type or set of attribute types instead of a primary or candidate key. Consequently, the search key values do not uniquely identify a single record. Each index entry consists of a search key value as well as the address of the first block that contains records with this key value. If there is an index entry for each unique value of the search key, the index is dense. If only some search key values are indexed, the index is sparse. The search process is the same as with a primary index, except additional sequential block accesses may be required after the first random block access to the data file to retrieve all subsequent records with the same search key value. In this example, a clustered index is defined over the search key country. A search for all records with UK as the value for country requires random block accesses to search the index and retrieve the second block in the file, which is the first to contain customers from the UK. In addition, a sequential block access to the third block is required, which contains UK customers as well. Note that just like primary indexes, clustered indexes have the additional complexity of keeping the index up to date if records in the data file are inserted or deleted, or if their search key value is updated. A frequently used variation is to start a new block in the data file for every new value of the search key. This is less efficient in terms of storage space, as many blocks will not be filled up entirely. On the other hand, it alleviates the maintenance problem to an extent because there is room to add records with the same key value to a block without reorganizing the data file nor the index. Another option to avoid too frequent file reorganization, which is also applicable to primary indexes, is to provide a separate overflow section for records that cannot be stored in the appropriate position in the regular sequential file. However, as with random file organization, records being positioned on a different location than where they were initially expected results in additional block accesses, which has a negative impact on performance. Creating an index to an index results in multi-level indexes. In practice, many index levels may occur. We illustrate a case with 2 index levels in this figure. Each index is searched according to a binary search, yielding a pointer to the appropriate block in the lower level index. The lowest level index yields a pointer to the appropriate block in the data file. In the case of a primary index, all block accesses are random block accesses. With a clustered index, additional sequential block accesses on the data file may be called for to retrieve subsequent records with the same search key value. Note that the number of random block accesses on the higher level indexes remains limited, since they are sparse indexes and can be kept limited in size thanks to the multiple levels. In addition, higher level indexes can often be kept and searched in memory, resulting in even more efficient processing. A primary index and clustered index can never occur together for the same file, as it is important to choose the most appropriate index to base the physical ordering of the records on. Nevertheless, in addition to a primary index or a clustered index, it is possible to create additional indexes over other search keys. They are called secondary indexes and have no impact on the physical ordering of the records, but do allow speeding up retrieval according to criteria other than the one used for the primary file organization. The use of indexes for secondary file organization is discussed later in this chapter. Also, all remarks made with respect to maintenance of indexes are even more pertinent in the case of multiple index levels. A list can be defined as an ordered set of elements. If each element has exactly one successor, except for the last element in the list, we call it a linear list. A linear list can be used to represent sequential data structures. All other types of lists are called nonlinear lists. These can be used to represent tree data structures and other types of directed graphs. In what follows, we only focus on the use of lists to represent sequential data structures and tree data structures. In both, the ordering can be represented by means of either physical contiguity of the data records or by means of pointers. A linear list embodies a sequential data structure and can be represented in 2 ways. If the logical ordering of the records is expressed by means of physical contiguity, we have the sequential file organization method already discussed in this chapter. If, on the other hand, the logical ordering of the records is represented physically by means of pointers, we speak of a linked list. The simplest linked list method is the one-way linked list. In the latter, records are physically stored in an arbitrary order, or sorted according to another search key. A logical, sequential ordering is then represented by means of pointers, with each record containing a next pointer to the physical location of its logical successor. The pointers are embedded as additional fields in the stored records. To process the list, the first record is retrieved. The pointer to the next record is followed, and so on, until a record is reached that contains an end of list indicator instead of a next pointer. This is illustrated in the figure. As can be seen, each record contains a pointer to its logical successor. The logical order is independent from the physical ordering of the record. The end of list is indicated by an asterisk. Alternatively, the last record may contain a pointer that points back to the head of the list such that the list can be processed from any starting position. Linked lists make it possible to define one or more logical orderings over the same set of records independently of their physical ordering. They are often used to chain overflow records together. A possible disadvantage is that all records must be retrieved, even if only part of the list needs to be processed, because the pointers to navigate the list are embedded in the records. An alternative is to store the pointers separately in a directory as shown in the figure. A directory is a file that defines the relationships between the records in another file. As the pointers are much smaller than the actual data records, by storing them in a separate file, navigating them requires less block accesses and hence less time. Also, adding, updating, and deleting pointers is much easier in a separate file. Another variant is to combine a linked list with indexed addressing. The records are distributed into intervals, with each interval being represented by an index entry. The index allows for directly accessing the first record of an interval without passing through all the records in previous intervals. This is illustrated in the figure. To calculate the expected retrieval time of a linked list, we can use the same formulas we used for sequential file organization. The only difference is that all block accesses are random block accesses, since the logical successor of a record is no longer physically adjacent to its predecessor. Also, the impact of blocking is limited to non-existent, since the chance that logically related records are stored physically in the same block is quite small. Two disadvantages of a one-way linked list are the inability to return to a record's predecessor in an efficient way, and the fact that if one of the pointers is lost or damaged, the logical sequence of the list cannot be reconstructed. Both disadvantages are resolved with the two-way linked list method. In a two-way linked list, each record contains a prior pointer as well as a next pointer. In this way, the list can be processed efficiently in both directions. Moreover, the prior pointers add a measure of redundancy, which can be exploited to reconstruct the logical ordering if a pointer in the other direction is lost or damaged. Just like with the one-way linked list, a variant with a directory or an index is also possible. Here you can see a two-way linked list illustrated. A tree consists of a set of nodes and edges with the following properties. There is exactly one root node. Every node except for the root has exactly one parent node. Every node has 0, 1 or more children or child nodes. Nodes with the same parent node are called siblings. All children, children of children, etc. of a node are called the node's descendants. A node without children is called a leaf node. The tree structure consisting of a non-root node and all of its descendants is called a subtree of the original tree. The nodes are distributed in levels, representing the distance from the root. The root node has level 0. The level of a child node is equal to the level of its parent plus 1. All siblings have the same level. A tree where all leaf nodes are at the same level is called balanced. In that case, the path from the root node to any leaf node has the same length. If leaf nodes occur at different levels, the tree is said to be unbalanced. Tree data structures are relevant in several ways. First, they may provide a physical representation of a logical hierarchy or tree structure. An example is a hierarchy of employees. A second application of tree data structures is when they provide a purely physical index structure to speed up the search and retrieval of records by navigating the interconnected nodes of the tree. We denote this type of tree structure with the general term search tree. The most well-known representatives of this class are the B tree and B plus tree, which are dealt with in more detail later in this chapter. A first way to implement trees is by means of physical contiguity, where the physical position of the records along with additional information expresses the tree structure. The tree nodes are typically stored in a top-down left-right sequence, first the root, then the root's first child, then the child's first child if it exists, etc. If a node has no more children, its next sibling, from left to right, is stored. If a node has no more siblings, its parent's next sibling is stored. In order to reconstruct the tree structure, each node's level needs to be included explicitly, because the physical contiguity of two nodes doesn't discriminate between a parent-child and sibling-sibling relationship. This figure illustrates how a logical tree structure is represented physically in this way. The letters represent the record keys, the numbers denote the level in the tree for the physical records. Note that such a representation is only navigable in a sequential way. For example, it is not possible to directly navigate from node B to node C without passing through all of B's descendants. A linked list can also be used to represent a tree structure. Here, physical contiguity is complemented with pointers to improve navigability. The nodes are stored in the same physical sequence as described previously, but in addition, each node has a pointer to its next sibling if the latter exists. In this way, both parent-child and sibling-sibling navigation are supported respectively by accessing the physically subsequent record and following the pointer. Also, there is no need to store each node's level. This information can be inferred from the physical positions and the pointers. Still, for reasons of efficiency, a single bit is often added to each node, indicating whether the node is a leaf node, bit equals 0, or not, bit equals 1. You can see this illustrated here. Note that many variations are possible. Complementary techniques are needed to speed up access to data according to those search keys that had no impact on the physical ordering of the data. These techniques, which we refer to as secondary file organization, always involve indexes, called secondary indexes. In what follows, we discuss their characteristics, inverted files, multi-column indexes, and other index types. In contrast to a primary index or a clustered index, a secondary index is based on an attribute type or set of attribute types that is or are not used as ordering criteria of the actual data file. There can only be a single primary or clustered index for a data file, but in addition, there can be several secondary indexes. A secondary index's search key can be atomic or composite, consisting of multiple attribute types. It can be either a primary key or other candidate key, or a non-key attribute type or combination of attribute types. The index itself is again a sequential file which can be searched by means of the binary search technique. Here you can see an example of a secondary index on a unique search key. If the search key is non-unique, multiple records correspond to a particular key value. In that case, there are several possibilities. One option is to have a dense index, with an index entry for each record and thus multiple entries with the same key value. A more widespread alternative is to add a level of indirection, with each index entry referring to a separate block that contains all pointers to records with the corresponding search key value. In that case, we speak of an inverted file as discussed in the next section. Before continuing, let's assess the pros and cons of secondary indexes. There are additional constructs which need to be updated if the data file changes, but the performance increase they offer may be even bigger than with primary or clustered indexes. Indeed, because the data file is not ordered according to the search key of a secondary index, it would not be possible to conduct a binary search on the data file itself, and a full linear search of the file would be required if a secondary index was not available. For example, let's explore once more the sample file with 30,000 records and 1,500 blocks we introduced earlier. Suppose we are using a secondary index, defined over a unique search key. The index contains 30,000 index entries, one for each search key value. If we assume an index entry size of 15 bytes again, the blocking factor of the index is again 136. In that case, NBLKI equals the ceiling of 30,000 divided by 136, which equals 221 blocks. The expected number of block accesses to retrieve a record by means of the secondary index then amounts to logarithm base 2 of 221 plus 1, or about 9 random block accesses. Without a secondary index, it would take a full table scan. Let me do that again. Without a secondary index, it would take a full file scan. Hence, on average, 1,500 divided by 2 or 750 sequential block accesses to find the record according to the search key. An inverted file defines an index over a non-unique, non-ordering search key of a dataset. There is one index entry per key value, and hence each entry may refer to multiple records with the same key value. The index entries have the following format: key value and block address. The block address refers to a block containing record pointers or block pointers to all records with that particular key value. This approach requires an additional random block access to the block with pointers to records that correspond to an index entry. However, it allows avoiding the creation of a large, dense index. Also, queries that involve multiple attribute types can be executed efficiently by taking the intersection of the blocks with pointers corresponding to an individual attribute type. This is illustrated here. Here we show an example of an index over a composite search key, resulting in a so-called multi-column index. If certain combinations of attribute types are often used together in a query, it can be advantageous to create a multi-column index over these attribute types. This principle can be applied to both primary, clustered, and secondary indexes. In case of a secondary index, if the composition of the index attribute types is not a primary key nor a candidate key, the inverted file approach can be used as discussed in the previous section. An example is given in the figure here. The search key consists of the country and gender attribute types, and all index entries consist of combinations of country-gender values. Since the combination is non-unique, and since the data records are not sorted according to the search key, the inverted file approach is used with intermediate blocks containing all pointers to data records with a certain country-gender combination. Note that the index can be used to efficiently retrieve all records with the desired country-gender values. Also, all people living in a certain country, regardless of their gender, can be retrieved efficiently since all index entries pertaining to the same country are adjacent. However, retrieving all males regardless of the country will not be so efficient since all index entries for people with the same gender are scattered throughout the index. Hash indexes provide a secondary file organization method that combines hashing with indexed retrieval. The index entries have the same format as with a normal secondary index. They consist of key value pointer pairs. Yet, the index is not organized as a sequential file, but as a hash file. Applying the hash function to the search key yields the index block where the corresponding index entry can be found. Based on the pointer in this entry, the actual record or records can be retrieved. Another index type worth mentioning is the bitmap index. Bitmap indexes are mostly efficient for attribute types with only a limited set of possible values. Instead of these values, bitmap indexes contain a row ID and a series of bits, one bit for each possible value of the indexed attribute type. For each entry, the bit position that corresponds to the actual value for the row at hand is set to 1. The row IDs can be mapped to record pointers. Bitmap indexes for the country and gender attribute types are represented in this figure. When looked upon vertically, each column can be considered as a bitmap or bit vector indicating which tuples have the values indicated by the column. By applying Boolean operations to bit vectors from multiple bitmap indexes, it becomes very efficient to identify records that satisfy certain criteria, such as male customers that live in the UK. A last example of a specific index type is the join index, as supported by some RDBMSs. The latter is a multi-column index that combines attribute types from 2 or more tables in such a way that it contains the pre-calculated result of a join between these tables. In this way, join queries can be executed very efficiently. B trees and B plus trees are tree-structured index types that are heavily used in many commercial database products. Before discussing them in detail, we position them in the general context of multi-level indexes and search trees. Multi-level indexes are very useful for speeding up data access if the lowest level index itself becomes too large to be searched efficiently. An index can be considered as a sequential file, and building an index to the index improves the access to the sequential file. This higher level index is again a sequential file to which an index can be built, and so on. This principle can be applied to primary, clustering, as well as secondary indexes. The lowest level index entries may contain pointers to disk blocks or individual records. Each higher level index contains as many entries as there are blocks in the immediately lower level index. Each index entry consists of a search key value and a reference to the corresponding block in the lower level index. Index levels can be added until the highest level index fits entirely within a single disk block. In this context, we speak of a first level index, second level index, third level index, etc. With a binary search on a single index, the search interval, consisting of disk blocks, is reduced by a factor 2 with every iteration, and therefore it requires approximately log base 2 NBLKI random block accesses to search an index consisting of NBLKI blocks. One additional random block access is needed to the actual data file. With a multi-level index, the search interval is reduced by a factor BFI with every index level, BFI being the blocking factor of the index. BFI denotes how many index entries fit within a single disk block, resulting in a single entry for the higher level index. This reduction factor is also called the fan-out of the index. Searching a data file according to a multi-level index then requires log base BFI of NBLKI plus 2 random block accesses, with NBLKI denoting the number of blocks in the first level index. This formula can be derived as follows. We need to add index levels until the highest level index fits within a single disk block. The number of required blocks for index level I can be calculated as follows. NBLKI subscript I equals NBLKI subscript I minus 1 divided by BFI and rounded upwards towards the nearest integer for I equals 2, 3, and so on. By applying the previous formula I minus 1 times, we derive that NBLKI subscript I equals the ceiling of NBLKI divided by BFI raised to the power I minus 1 for I equals 2, 3, and so on, and with NBLKI the number of blocks in the lowest level index. For the highest level index, consisting of only one block, it then holds that 1 equals the ceiling of NBLKI divided by BFI raised to the power h minus 1, with h denoting the highest index level. Therefore, h minus 1 equals the ceiling of log with base BFI of NBLKI, and hence h equals the ceiling of log with base BFI of NBLKI plus 1. The number of block accesses to retrieve a record by means of a multi-level index then corresponds to a random block access for each index level, plus a random block access to the data file, which thus equals to the ceiling of log with base BFI of NBLKI plus 2. BFI is typically much higher than 2. So using a multi-level index is more efficient than a binary search on a single level index. Let's apply these insights to the same 30,000 record sample file. Suppose we retain the lowest level index from the secondary index example. In other words, a secondary index over a unique search key. The index entries are 15 bytes in size and BFI is 136. The number of blocks in the first level index, NBLKI, equals 221. The second level index then contains 221 entries and consumes the ceiling of 221 divided by 136, or 2 disk blocks. If a third index level is introduced, it contains 2 index entries and obviously fits within a single disk block. Searching a record by means of the multi-level index requires 4 block accesses, 3 to the respective index levels, and 1 to the actual data file. This can be calculated as follows: the ceiling of log with base 136 of 221 plus 2 equals 4. Remember that 9 random block accesses were required when only using the lowest level index. In practice, it would probably be more efficient to use only a second level index and first level index, with the second level index maintained and searched in internal memory. A multi-level index can be considered as a so-called search tree, with each index level representing a level in the tree, each index block representing a node, and each access to the index resulting in navigation towards a subtree in the tree, hence reducing the search interval. The problem is that multi-level indexes may speed up data retrieval, but large multi-level indexes require a lot of maintenance if the data file is updated. Hence, traditional multi-level indexes have quite a negative impact on update performance of the database. For that reason, so-called B trees and B plus trees are a better alternative. They keep the essence of a search tree, but leave some space in the tree nodes, or disk blocks, to accommodate for inserts, deletions, and updates in the data file without having to rearrange the entire index. We discuss them in the next sections. The functioning of B trees and B plus trees is easier to grasp if we first introduce the concept of binary search trees. A binary search tree is a physical tree structure where each node has at most 2 children. Each tree node contains a search key value and maximum 2 pointers to children. Both children are the root nodes of subtrees, with one subtree only containing key values that are lower than the key value in the original node, and the other subtree only containing key values that are higher. Navigating a binary search tree is very similar to applying the binary search technique already discussed in the context of sequential file organization. Here also, search efficiency is improved by skipping half of the search key values with every step, rather than linearly navigating all key values. Now the search space is not narrowed by splitting the physical range of addresses in half as with the binary search technique, but by navigating a tree structure and in each node choosing between a left and a right subtree. More concretely, suppose a search key k is used with values ki. To find a node with search key value kmu, the key value ki in the root node is compared to kmu. If ki equals kmu, the search key is found. If ki is strictly bigger than kmu, then the pointer to the root of the left subtree with only key values lower than ki is followed. Otherwise, if ki is strictly less than kmu, the pointer to the root of the right subtree is followed. This subtree contains only key values higher than ki. The same procedure is applied recursively to the chosen subtree until the node with kmu is found or until a leaf node is reached, meaning that the key value kmu is not present in the tree. This is illustrated in this figure, with kmu equaling 24. The appropriate node is found after 3 steps, whereas a linear search would have taken 9 steps in this case. As already discussed in the context of binary search, this performance gain becomes larger as the number of key values increases. A B-tree is a tree-structured index. B-trees can be considered as variations of search trees that are explicitly designed for hard disk storage. In particular, each node corresponds to a disk block, and nodes are kept between half full and full to cater for a certain dynamism of the index, hereby accommodating changes in a data file without the need for too extensive rearrangements of the index. Let me do that sentence again. In particular, each node corresponds to a disk block, and nodes are kept between half full and full to cater for a certain dynamism of the index, hereby accommodating changes in the data file without the need for too extensive rearrangements of the index. Every node contains a set of search key values, a set of tree pointers that refer to child nodes, and a set of data pointers that refer to data records or blocks with data records that correspond to the search key values. The data records are stored separately and are no part of the B-tree. A B-tree of order k holds the following properties. Every non-leaf node is of the following format: B0, K1, PD1, B1, K1, PD2, up to KQ, PDQ, PQ, with Q less than or equal to 2K. Every PI is a tree pointer. It points to another node in the tree. This node is the root of the subtree that PI refers to. Every PDI is a data pointer. It points to the record with the key value KI or to the disk block that contains this record. A B-tree is a balanced tree. All leaf nodes are at the same level in the tree. Every path from the root of the B-tree to any leaf node thus has the same length, which is called the height of the tree. Leaf nodes have the same structure as non-leaf nodes, except that all their tree pointers PI are null. Within a node, the property holds that K1 is strictly less than K2, and so on, strictly less than KQ. For every key value x in the subtree referred to PI, the following holds. Key I is strictly less than x is strictly less than Ki is strictly less than x is strictly less than Ki plus 1 for 0, strictly less than I strictly less than q. X is strictly less than Ki plus 1 for I equals 0, and Ki is strictly less than x for I equaling q. The B-tree's root node has a number of key values and an equal number of data pointers that varies between 1 and 2k. The number of tree pointers and child nodes then varies between 2 and 2 times k plus 1. All normal nodes, or in other words internal nodes or non-root and non-leaf nodes, have a number of key values and data pointers between k and 2k. The number of tree pointers and child nodes varies between k plus 1 and 2 times k plus 1. Every leaf node has a number of key values and data pointers between k and 2k and no tree pointers. If the index search key is non-unique, a level of indirection is introduced similar to the inverted file approach discussed previously. The data pointers PDI then don't point to the records directly, but to a block containing pointers to all records satisfying the search key value Ki. This figure provides a few simple examples to illustrate the principles of B-trees with varying order and height. The numbers represent key values Ki, whereas the arrows represent tree pointers Pi. The data pointers PDI are not depicted so as to not clutter the illustration, but in reality there's a data pointer for every key value. B tree is searched recursively starting from the root. If the desired key value x is found in a node, say ki equals x, then the corresponding data record or data records can be accessed in the data file by following the data pointer PDI. If the desired value is not found in the node, a tree pointer is followed to the subtree that contains the appropriate range of key values. More precisely, the subtree pointer pi to be followed is the one corresponding to the smallest value of I for which x is strictly less than ki plus 1. If x is strictly bigger than all ki, then the tree pointer pi plus 1 is followed. The same procedure is repeated for the subtree and so on, until the desired key value is found in a node or until a leaf node is reached, meaning that the desired key value is not present. This approach is again very similar to a binary search algorithm, but since the number of tree pointers is much higher than 2, the fan out and therefore search efficiency is much higher than with a binary search. Note that the capacity of a node equals the size of a disk block and that all nodes except for the root are filled for at least 50%. Hence, a B tree uses the storage capacity efficiently, but still leaves room for additions to the data file without the need for impactful rearrangements of the index structure. It is very complex to make exact predictions about the required number of block accesses when searching a B tree. There are many possible configurations. Every node may contain between k and 2k key values except for the root, and the tree may assume different shapes depending on node splits and mergers. Sometimes B trees are also used as primary file organization technique, hence organizing the actual data file as a search tree. The nodes then still contain search key values and tree pointers. However, instead of data pointers, they contain the actual data fields of the records that correspond to the search key values. This approach can be very efficient with small files and records with a very limited number of fields. Otherwise, the number of tree levels quickly becomes too large for efficient access. Most DBMS implementations use indexes based on B+ trees rather than B trees. The main difference is that in a B+ tree, only the leaf nodes contain data pointers. In addition, all key values that exist in the non-leaf nodes are repeated in the leaf nodes, such that every key value occurs in a leaf node along with a corresponding data pointer. The higher level nodes only contain a subset of the key values present in the leaf nodes. Finally, every leaf node of a B+ tree also has one tree pointer pointing to its next sibling. In this way, the latter tree pointers create a linked list of leaf nodes, sequentially arranging all leaf nodes according to the key values they contain. This figure presents some simple B+ tree examples with the same order and search key values as the B tree example. Again, the data pointers, which now only exist in the leaf nodes, are not represented. Note that, in contrast to B trees, the B+ trees contain some redundancy in their search key values. Note also the next tree pointers in the leaf nodes. Sometimes, previous pointers are present as well. Searching and updating a B+ tree occurs in a similar way as with a B tree. Note that, since only the leaf nodes contain data pointers, every search must continue until the leaf nodes, which was not the case with B trees. Still, B+ trees are often more efficient, because the non-leaf nodes do not contain any data pointers, so with the same block size their ordering can be higher than with a B tree. As a consequence, the height of a B+ tree is often smaller, resulting in less block accesses to search the tree. In most cases, the leaf nodes of a B+ tree, which do contain data pointers, have different order than the other leaf nodes. It is worth noting that other variants exist as well. In particular, there are variations on the fill factor, which denotes how full a non-leaf node must be, and which is 50% for standard B trees and B+ trees. For example, a B tree with a fill factor of 2/3 is often called a B* tree. In this chapter, we dealt with different aspects pertaining to physical file organization. First, we presented the characteristics of storage devices and how these affect the performance of physical data access. Then we discussed the organization of respectively stored records and physical files. We distinguished between primary and secondary file organization methods. In this context, special attention was paid to different types of indexes and the way in which they improve search performance. B trees and B+ trees in particular were discussed as index types that often occur in DBMS products. If you want more information, I'm happy to refer you to our book, Principles of Database Management. You can find also more information at the website indicated at the bottom of my slide.